Alright, so in this lesson we're going to be looking at a bunch of basic functions and then we're going to apply a radical square root to each function and see how that changes the graph. We're also going to look at, given some random graph, how we could draw the radical function of it. Okay, first things first, you guys need to change your window settings to these. We're going to be using our calculator for the exploration. So we're going from -2 to 2 on both the x and the y-axis. Booker, did you just drool? Oh, I thought I heard like...
No, it was just me sucking wind.
So sad.
I hope you get sick now, yeah. I hope you get sick. Feel my pain. Thanks, Jared.
Lovely singing voice. Okay, so we have our window settings in, yeah?
Yeah.
We're going to be comparing these the initial graph y equals f of x to the radical function of that graph. Okay, so the first graph you're going to put in your y equals is x squared. And the radical function, that just means the square root. So we're going to take the square root of x squared. And then we can graph. The first graph that pops up will be the one that's already drawn for you right here. The second one is the radical function. So if we were to do a basic drawing, it's something like that. Okay, so just make sure you draw that. Alright, domain of the original graph, what did we get? All real numbers. And what's the range of the original graph?
Greater or equal to 0.
You got it. Okay, what's the domain of our radical function? All real numbers. What's the range of our radical function? Y is greater than or equal to 0. Nothing changed there. The shape changed, but the domain and range didn't. Okay, next graph. They're telling us that we have y equals f of x. F of x is x cubed. That's this shape here. The square root of f of x would actually be the square root of x cubed. So we're just going to change our y1 and y2 and see what happens. So we have x to the power of 3, and then the square root of x to the power of 3. Once you have that in, just graph it. This is our original function coming up, and that's our radical function. So what's the domain of the original function? X is an element of all real numbers, and your range? All real numbers. What is the domain of your new function? Greater than or equal to 0, perfect. And your range? Greater than or equal to 0. Alright, our third function we're going to compare is the function of x plus 1, which means the radical function would be the square root of x plus 1. X plus 1 is just a line. Let's talk about the domain. Element of all real numbers. Okay, the range of that? All real numbers. Now let's see what happens when we take the square root. We had x plus 1 as our original function, and the square root of x plus 1. That's our radical function. Okay, so our original function was the line. Our radical function is this concave down line. What is the domain? How'd you get the -1? Good, so if you look at the original graph, x plus 1, set that equal to 0, then the x-intercept would be -1. Okay, so x is greater than or equal to -1, and our y, one more time, is greater than or equal to 0. Do you guys notice that consistency for our radical functions? The range has been the exact same. Now before we move on, have you guys noticed any trend between this graph and this graph and what happened to this negative portion here? Disappeared, and why would that be? Okay, nothing happened here, and nothing happened here. Where did it go? Yes, exactly, Jackson. You can't have a negative square root. So that means all the values below the x-axis are not going to exist. Let's keep going. There's a few more radical functions we're going to compare. Okay, so could you guys put in your y equals the absolute value of x? I've got to start all over because I closed my calculator down. So just a reminder, you go math and then over to number to get your absolute value. Plug an x in there. And then we want to take the square root of the absolute value. Math and then slide over to number. And then press enter for absolute. And then put an x in there. The brackets close it. Okay, let's graph it. Here's our absolute value of x, and here's the radical of the absolute value of x. So we're getting a few curved lines. Looks like that. The original function had a domain of any real number and a range of y is greater than or equal to 0. The radical function had those same domain and ranges. So x is an element of all real numbers, y is greater than or equal to 0. Nothing changed on that one. Now let's look at the logarithm. This is the base logarithm of x here. What is the domain? Do you guys remember anything about vertical asymptotes with logarithms? Where is that vertical asymptote? Y-axis, or x equals 0. So because it's an asymptote, the graph is going to be approaching it, but it's not going to actually touch 0. So our domain of the original graph is x is greater than 0. It's not equal to, just greater. And what's your range? All real numbers. It's going to infinity and negative infinity. So let's compare the logarithm to the radical logarithm. So log x and the absolute value, or sorry, the radical of log x. Graph it. Again, that negative piece is not included, just this portion here. So the domain, do you guys remember the x-intercept for log x? 1, you got it. Okay, so it happens to start at that x-intercept. So x will be greater than or equal to 1, and the range is y is greater than or equal to 0. Okay, next one we have an upside down parabola. Negative x squared minus 1. We take a look at the function. Domain is an element of all real numbers. And range, how are we going to solve for that? How are you gonna get that y-intercept? Plug 0 in for x, we get 0 minus 1, so it's at negative 1. Y will be less than or equal to negative 1. So y1 is negative x squared minus 1. And then we're taking the square root of that. Any predictions? What's going to happen? What's your prediction?
Won't work.
Won't work. Why?
Negative.
Good. So everything on that graph is below the x-axis. So there's our first graph, and nothing's coming up for the radical. No graph exists. So the next example is pretty much repeating what we've been doing. So I'm going to skip over that, and let's just go to number 3. So in which of the previous examples from question 1 are the domains and the ranges the exact same for the original function and the radical function? So take a look at the domain and ranges that we listed. Which graphs have the exact same domain and range? Okay, first one. And? Third one? Let's check that. I don't know if I agree.
Maybe it's the fourth one.
Sure, Chris?
Not the mirror, I don't know.
Fourth one? Yes.
Okay, the third one, they definitely have different domain and ranges. But the fourth one, yes. Good. Okay, so the first graph and the fourth graph, they had the exact same domain and range. Can you guys summarize for part B what they have in common, why they would have the same domain and range?
Oh, they're all positive.
Good, both graphs. So f of x and the square root of f of x exists above the x-axis. In other words, we can say that f of x is greater than or equal to 0, and the square root of f of x is greater than or equal to 0. So if those graphs are on the x-axis and above, they're going to have the same domain and range. So for part C, it's a bit of filling in the blank, but I'm just going to get right to the facts. Okay, if you flip to the next page at the bottom, talking about graphing the square root of f of x from the graph of y equals f of x, there's a few things, few relationships that you're going to note. So I think we've already realized this. When the graph of the original function is less than 0, this graph does not exist. So you might want to write below the x-axis. So for example, when we had the graph of x cubed, what happened to the negative piece? It did not exist. The radical only happened here. This piece didn't go anywhere. It just doesn't exist for the radical function. Okay, next statement. When f of x equals 0, okay, that's basically saying when you have an x-intercept, the square root of that function also has the same x-intercept, which means they're invariant points. So let's just take a look at the graph of the polynomial x cubed again. Okay, when we had an x-intercept 0, 0, did that x-intercept stay in the same place? Yes, it remained at 0, 0.
Hello, just keep on, I'm gonna get your envelope.
Oh,
We're
okay.
counting money.
Sounds good. I have a few students who are handing in their money to the office.
Okay, I got the office envelope.
Okay,
Because we have to get a check written for Mr. Fowler.
perfect.
Okay, thanks.
Thanks. Okay, so this is saying when f of x is equal to 0, you take the radical function and you will have that same x-intercept, and we call those invariant points. Similarly, when the original graph is equal to 1, so when y equals 1, the square root of 1 is 1. So again, we have 1. And that's happening right here. Okay, that graph will also, or that point will also be invariant. So we have two invariant points, an x-intercept and at y equals 1. And if it's not clicking quite yet, don't worry, we're going to go through a few examples to stress this, okay? When we have y is between 0 and 1, the graph of the radical will lie above the graph of the original function. So for example, if this is 1 here, we're between 0 and 1 right here. Notice that the radical is above the original. Okay, when you're between 0 and 1, the radical will be above it. When we are greater than 1, so anything above y equals 1, the graph will be below the original function. So you're probably wondering, well, why is that? If you were to take the square root of, say, negative 0.5, what do you get? Calculate.
.707.
It equals 0.707.
07.
Okay, so is that bigger than 0.5? Yeah, which means it would fall above. Okay, whereas if you took, say, anything greater than 1, so for example the square root of 4, you get a number smaller than that original value, which means it will fall below where the graph existed. Okay, so if you can memorize that rule, great, but if not, you can always calculate your y-coordinates to see where they would go. Okay, the values of the square root of f of x are the square roots of the values of f of x, and if possible, when you're graphing, you're just going to try and choose obvious points, like the square root of 4, the square root of 9. It's easier to calculate. Another thing to note is that basically when you're taking the square root of f of x, whenever there's straight portions, so I'll just go to the absolute value here. Okay, when we have the absolute value, when we take the radical of that, we're going to have a concave shape go through the graph. It's going to concave down. And similar on this side, concaving down. So whenever you have straight lines on your original function, the radical function will concave down. So that's a little summary of how we would draw the features. I just want to go back to number 4 and go through these two examples. So just above where we were. Okay, the original graph was y equals x plus 1. Okay, and the radical function is the square root of x plus 1. What do you guys notice happened to this piece here? It's gone. It does not exist on the radical function. Okay, what about these points here? What do we call those? Invariant points. They occur at the x-intercept and when y equals 1. When we have values between 0 and 1, the graph will exist above and it will concave down. So the radical function exists above the original function. When we are looking at numbers bigger than 1, the radical function exists below the original function. Okay, similarly here, there wasn't anything below the x-axis, so we don't have to worry about that. But we have invariant points at the x-intercept, as well as when y equals 1, y equals 1. Where the graph exists between 0 and 1, the radical function will be above the original graph, and where the original function is greater than 1, the radical function will exist below. and below. So to really make sure that's ingrained in, flip to the next page, and before, or as we go through it, what I'd like you guys to do, please, is to just make note of these steps on this page. First step for drawing a radical function is we have to omit the graph below the x-axis. Okay, so write that step down. Step 1, omit the graph below the x-axis. So when we take a look at this graph, anything below the x-axis, we can just wipe out. Okay, get rid of that. It's not going to be part of our radical function. Okay, same thing over here. Anything below the x-axis, we're going to omit. It's not going to be included in our radical function. Step 2, we're going to find our invariant points. Those exist at our x-intercepts, so along the x-axis, as well as when y equals 1. So we have an x-intercept here. That's going to be an invariant point. X-intercept here, and x-intercept here. Those are all invariant points. The other invariant points are when y equals 1. So taking a look at our scale, we're going up by 1. So let's just figure out on the original graph where y equals 1. Here, 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 and here. So in total, we have 7 invariant points. Okay, step 3, we want to look for our maximum points, and we're going to do a little bit of point mapping. X, y goes to x stays the same, but all the y values we take the square root of. So max points that I can see obviously are this top section. Y is at 4. So if I were to take the square root of 4, it'd now be at 2. So x stays the same, but y goes down to 2. X stays the same, y is down at 2. For these 4 points. Square root of 4 equals 2. Alright, over here, the y value is 2. So to figure out where it goes, we need to take the square root of 2. And that equals 1.4 something. Okay, so we're roughly about here. That's how we're getting that point.
What?
Step 4 and 5, we're figuring out where we're drawing the graph. So when y is between 0 and 1, we draw our radical graph above our original graph. So let's just draw an imaginary line here where y equals 1. You don't have to draw it if you don't want to, but just following along. So when we're between, maybe I'll draw 2 imaginary lines. Okay, let's block off 0 and 1. Okay, when we're between there, we have to draw a radical function above the original graph. See how we're above that original line? And we had a straight line originally, so we're concaving down. Then when we're above 1, we should be below the graph, which makes sense because we need to connect the dots. Then we can go straight through these. And we need to connect this dot to this dot, which exists below the graph. Again, we're between 0 and 1. So the radical function will exist above the graph. That should be a nice smooth curve. I haven't really drawn it that way. Going from the x-intercept to y equals 1, we're between 0 and 1, so we draw above the original graph. And then we're going past 1, so we draw below it, connect it to that dot. Draw below it, connect it to the next dot, and we're between 0 and 1 again, so we draw it above the original graph. And we're done. We've drawn our radical function.
So weird.
It is a little weird, isn't it? But if you follow this set of rules that we have here, and I recommend if you didn't get it down, take a screenshot or a photo of those steps.
Bruce.
It will help out.
Bruce.
Um,
It's not quick.
another little hint is they're pretty much all right here.
Sum total, so you take a picture.
Okay, so on the page before it says graphing the square root of f of x given the graph. These are pretty much the steps I've listed. That's just a little more in English.
I prefer English.
Yeah. So let's compare the domain and range of the original graph. Maybe I should line it up. There we go. Okay, what's the domain of the original graph? Keep in mind we had little arrows at the end.
All real numbers.
Okay, x is an element of all real numbers. And on the original graph, what was the highest point?
4.
4. So because it's going down forever and ever, y will be less than or equal to 4. What's the domain of our new graph?
All real. No. Oh, sorry, greater than 0.
Stops here at -3, goes all the way to +16. So our domain will be x is less than or equal to 16, but greater than or equal to -3. Okay, and the range? What's the highest point now? Good, it's up at 2. So y will go between 0 and 2. We're probably going to run short on time, but I'm going to try and do one more example because this definitely takes practice. Let's do... Let's do the first one because I think it could be a little more confusing than the second one. Hey, do we have any portion of the graph that we need to omit? Do I have any x-intercepts for invariant points? Do I have any y equals 1 for invariant points? No. So I don't have any specific points. What do I have to do with all the y coordinates that I see? Take the square root. Good. So -2, 3 will go to -2 square root 3. And what's the value of the square root of 3?
0.7.
Trying to draw an even scale here. Sorry, what did you say?
1.7.
1.7. So roughly here. Okay, that's -2 square root 3. Okay, and 0, 6. What is the square root of 6? Anyone with a calculator? Square root of 6.
2.4.
2.4. Good guess. Okay, so our y-intercept's now at 0 and the square root of 6, which is 2.4. We already took the square root of 3. It's at 1.6, right? So we are now at 6 and the square root of 3. And the arms keep going on forever. Oh, I missed 1 point. 2, 9. The square root of 9 is 3. 1, 2, 3. So last thing we need to do, just thinking about it, all these points are above 1, right? So that means that our graph has to be below the original graph. So we're just going to connect the dots and then put their arms on the end.